Hello, in this video we will generate the Taylor Maclaurin SERIESSUM expansion of the exponential cumulative distribution function, also known as EXPONDIST of x comma lambda comma 1. So it's the value of this exponential cumulative distribution function with this definition is 1 minus e to the negative lambda x. And we will regress it to the fourth degree linear polynomial regression. And let's generate the data set of EXPONDIST over the range of x sub 0 to 1.3. So RA formula, EXPONDIST of the x values where lambda is 3, and we choose 1 as the last argument because this is cumulative, this is exponential cumulative distribution function. And here we have the trend line where it is regressed to a polynomial regression to the power 4. So we'll calculate the values of B0, B1, B2, B3, and B4 using LINEST. Next, we'll use the definition of the exponent, which is 1 minus e to the negative lambda x. So we begin with the exponent. So RA formula, exponent of the x values. Then we factor in the negative lambda. We start with the negative first, negative 1. And then we factor in lambda. So multiply lambda. So this is a decaying function, while this is saturating of the two function. So we change that. We'll factor in 1 minus exponent negative lambda x. So this will be 1 minus exponent lambda x. Now they have the exact same values of the data set. These values match exactly because this is the definition of the EXPONDIST function. We'll generate the approximation of these two using the Taylor Maclaurin SERIESSUM, which is defined as 1 minus the exponent, which is the summation series sum of a times lambda x to the power n, where a is the coefficient, which is equal to negative 1 to the power n over n factorial, and the values of n will start from 0 to infinity. In this case, since it's only an approximation, we can limit up to 13, n equals 13. Now we enter the Taylor Maclaurin series sum, which is RA formula, series sum of x values, but this time it's multiplied by lambda. So times lambda raised to the power starting from 0 because our n value starts from 0, and our powers are incremented by 1. X to the 0, x to the 1, x squared, x cubed. So it's incremented, the powers incremented by 1. And this is the coefficient, this range. Now that we have the Taylor Maclaurin series sum column, we now work on the coefficient. So RA formula, we start with the denominator factorial of the n values. Now that we have the denominator, we'll work on the numerator part, negative 1 to the power n. Since it's a decay, we want this to be saturation like this. So we have to factor in 1 minus. So this will be 1 minus series sum. 1 minus the series sum. Now they are on the same line. And the values of the expansion is a good approximate because the values here up to the first 3, the first 4, they're exactly the same but there's an error at 0.04. As you go higher, there is an error. But still, the error is very small that the green line covers both red and blue lines. So we will calculate the values of B0, B1, B2, and B3 using LINEST. To do that, we will complete the 1 comma x matrix, which is this matrix, where this is the x to the 0 column, x to the 1 column, x squared, x cubed, and x to the 4th column. So this will be, the power will be transpose of the of the n up to 4. So we have 4. Now we can enter the array formula. Complete the 1 comma x matrix, which is array formula of the x values to the power of these values, sub 0 to 4. Enter. Now that we have the 1 comma x matrix, we can use the LINEST. So LINEST data y, because they are identical, we'll use the original and compare with the expansion, the approximate, comma, data x. And the Taylor Maclaurin series expansion will be, LINEST for that is data y and data x. So our B0 matches to our equation, or our trendline equation. B1, 2.88, also match to our trendline equation. B2, negative 3.66, negative 3.67, negative 2. They also match to our trendline equation. B3, you expect an error. So B3, 2.312, still matches to our trendline equation. And B4, negative 0.579, negative 0.572. So this completes the LINEST Polynomial Regression to the 4th degree and the generation of the Taylor Maclaurin series sum expansion for exponential cumulative distribution function.